In today's class, we are going to do operation on sets, and we'll also learn about Venn diagram. So the first operation that we learn about is union of sets. So A union B, we denote union by the sign U. A union B is equals to X such that X belongs to A or X belongs to B. Basically, we'll take the collection of all the elements that are there in A as well as that is present in B. So what does it look like in terms of Venn diagram? See, this is set A. See, this is set B. See, these are the common elements that are present in A as well as in B. So A union B basically denotes this whole portion, and this whole, the outer, this one that we see, this box, is the universal set denoted by U. So this denotes A union B. There are some properties of union that we need to study. First of all, A union B is equals to B union A. This is the commutative law. Second, we have is A union B. Union C is equals to A union B union C. First you take A and B's union and then C's union, or you take B and C's union and then with A union, it will get the same result. So this is called the associative law. The third one is if you take A and you union it with phi. Phi is basically an empty set. So any set union phi will become the set itself. This is called the identity law, where phi is the identity. 4. A union with A, you will get back A, because the elements that are present in A and A, if you take them together, you will get back the same elements that is there in A. This is called the idempotent law. And the last, number 5, is if we union A with the universal set. Here U denotes the universal set. So universal set union A is the universal set itself. Because if you take the whole universal set and you take A, say, so if you take their union, so you will get back the whole universal set. We are taking all the elements that is present in the universal set and A together, so we will get back the whole universal set. Second operation on sets that we are going to deal with is the intersection of sets. Intersection of sets is denoted by opposite U, the inverted U. So A, say there is a set A, intersection a set B will be equals to X such that X belongs to A and X belongs to B. Here and denotes means the terms or the elements that is common in both A and B. It should be present in A as well as it should be present in B. So how does its Venn diagram will look like? The whole set is the universal set. See, this is A. See, this is B. A intersection B means the elements that is common in A and B. So these are the elements that will be common in A and B. Hence, this portion is called the intersection portion of A and B. These diagrams are called Venn diagrams. VENN diagram. You don't need to mention it. This is just for your clarification. Venn diagram. Again, there are some laws. First one, A intersection B is equals to B intersection A. You take common elements of A and B, or you take the elements that is common in B and A, you get the same elements. So this one is the commutative law. Try and remember union as addition, or you can say the word or. Union corresponds with or and also corresponds with the addition. Intersection corresponds with and also corresponds with multiplication. The functions that we'll be using, the properties that we'll be seeing will be quite similar to multiplication for intersection and addition for union. Second law is the associative law, where A intersection B intersection C is equals to A intersection B intersection C. This is our associative law. Number third, A intersection phi is equals to phi, because common elements between A and phi is phi. There is nothing that is common between A and an empty set. Hence the resultant will become phi. Number 4, A intersection A is A. Number 5, A intersection, the universal set is also A, because the elements common in the universal set and A will only be A. And the last law is A intersection B union C is equals to A intersection B union A intersection C. This is called the distributive law and is quite similar to A into B plus C is equals to A into B plus A into C. Please do not mention plus, multiplication and plus. Use this for your understanding of intersection and union. A note: if say B is a subset of A union B will become A and A intersection B will become B. Let's look at Venn diagram. Say this is the universal set. This we have as A. So B is a subset of A. So all the elements that is present is B is also present in A. So this is our B. So A union B, if we take the union of A and B, we will get back this whole set A union B. That is basically A. And A B is a subset of A, so we are taking all the elements that is present in B is already present in A, and A might have some extra elements as well. So A intersection B, if we take the elements that is common in A and the elements that is common in B, so that will become only this portion, that is B. So A union B is A, and A intersection B is a set B. Third topic that we are going to deal is the disjoint sets. As the word suggests, when the intersection of two sets is phi, then we call the sets to be disjoint sets. Disjoint sets basically means that they are not joint. So universal set A, the set B. So here A intersection B is phi. There is nothing common in A and B. Hence the sets are disjoint sets. Number 4. Difference of two sets. So A minus B, or if we call it in words, that is basically only A. A minus B is equals to X such that X belongs to A and X does not belong to B. Means we are taking the set A and whatever elements are there in A that is also there in B, will remove them. So we can also write this as A minus of A intersection B, because the elements that is common in both A and B, that is what we are removing from the set A. So what this looks like is, say this is the universal set. We have two sets A and B. So A minus B is X such that X belongs to A and X should not belong to B. So the elements will be part of A, but none of the elements should be part of B. So this is what it will look like. We are just removing the intersection portion from the set A. So we can write A minus B as A minus of A intersection B. In a similar way, B minus A or only B will be X such that X belongs to B and X does not belong to A. So that is B minus A intersection B. So this set will look like we'll have this portion. From B, what we are removing is the intersection portion, or we are taking only the elements that is present in B and that is not present in A. So we are removing elements that is present in A and we are taking the portion that is present only in B. This is our difference of sets. This diagram is of A minus B and this Venn diagram is of B minus A. So this is the difference of two sets. The fifth operation that we are going to deal with is the complement of a set A. Denoted by A complement, or we can write as A complement. So this A complement is basically equals to the universal set minus the set A. So from the whole universal set, we'll remove the set A. This becomes our complement. So A complement, so this is the universal set. So A complement will be the elements that is present in the universal set, excluding the elements that is present in A. We are just removing elements that are present in A and we are taking the whole universal set. So, first law is that A union A complement will become the universal set, and A intersection A complement will be phi. So A is this, its complement is this portion. If we take the intersection, that is what is common between them, so we'll get the empty set. And if we take the union of A and with the complement, we'll get the whole universal set. Next important law is the De Morgan's law. A union B intersection is A intersection. A union B complement is A complement intersection B complement. What happens is union converts to the intersection sign, and if we take A intersection B complement, we get A complement union B complement. This law is the De Morgan's law. And some other basic things about complement is that A complement if we take, then we'll get back A, because A complement is this portion. So if we take the complement of A complement, we'll get back the set A. And the fourth one is that phi, the empty set's complement is the whole universal set, and the universal set's complement is phi. Now we'll deal with some questions relating the topics that we have dealt with. First example, let A is equals to 2, 4, 6, 8 and B is equals to 6, 8, 10, 12. Find number 1, A union B, and number 2, A intersection B. So to find the union, what we are going to do is we'll basically take the elements that is there in A and also the elements in B and we'll merge them together. So A union B will be 2, 4, 6, 8, 10, 12. So this elements contain all the elements that is in A and also that is there in B. Remember that in sets repetition does not make sense. So if you are writing 6 one time or we write 1000 times, it basically means the same thing. And A intersection B is what is common in A and B. So this set will contain 6 and 8, that is common in both A and B. Second example, let A is equals to A, E, I, O, U and B is equals to A, I, U. Show that A union B is A. Solution: A union B, if we take the elements in A and B together, what we get is A, E, I, A, E, I, O and U. So this is basically equals to A, the set A itself. Hence the proof. Also, you can take a note here that B is a subset of A. It is a smaller set as that of A. So, as B is a subset of A, what we are doing is when we take a union, A union B, we will get back A itself. As B was a subset of A, so A union B is A. So, this is what we are getting. As B is a subset of A union B, we are getting as A itself. Example 3. Let A is equals to 1, 2, 3, 4 till 10 and B is equals to 2, 3, 5, 7. Find A intersection B and hence show that A intersection B is basically B. Solution. So A intersection B, when we take 2, 3, 5, 7 is already present in A. A contains all the natural numbers from 1 to 10. So A intersection B will have 2 common, 3 common, 5 common and 7 common. So this is basically equals to B. So hence the proof. Just like we did over here, as B was a subset of A, so their union was equals to A. Here B is a subset of A, their intersection will be equals to B. Just like we discussed earlier in this note, A intersection B is B when B is a subset of A. Next example, example 4. Let A is equals to 1, 2, 3, 4, 5 and 6. B is equals to 2, 4, 6, 8. Find A minus B and B minus A. So A minus B will contain all the elements that is there in A and all the elements that in B will be excluded. So we have to remove 2, 4, 6 and 8 from the set A. So we'll remove 2, we'll remove 4, we'll remove 6. 8 is already not present in A, so it doesn't matter. So what we are left with is 1, 3 and 5. So this is our set A minus B. And B minus A will remove all the elements that is there in A which is present in B. So we are taking the set B and we are removing elements that is present in A. So 2 will get removed, 4 will get removed that is present in A, 6 will get removed that is present in A. So what we are left with is 8. So this is our B minus A. From here we also conclude that A minus B and B minus A are not equal. Example 5. Let V be equals to A, E, I, O, U and B be equals to A, I, K, U. Find V minus B, V intersection B and B minus V. So V minus B is equals to, we'll remove A here, we are removing I here and we are removing U. So we are left with E and O. V intersection B, the things that are common, A is common, I is common, U is common. So A, I, U. And B minus V, we are removing A from B, we will remove I, that is common, and we will remove U, that is common. So B minus V, we are left with K. So a thing to note over here is that the A minus B, A intersection B and B minus A, all these three are mutually disjoint. They have nothing in common. So A minus B, A intersection B, and B minus A. These three sets are mutually disjoint. None of them have any common elements. Example 6. Let U be the universal set of all students of class 11 of a co-educational school, and A be the set of all girls in class 11. Find A complement. Solution. So U contains all the students of class 11 of a co-educational school. So as A is the set of all girls in class 11, A complement is the set of all boys in class 11. Final example, example 7. Let U is equals to 1, 2, 3, 4, 5, 6. U we generally use to denote the universal set. A is equals to 2, 3 and B is equals to 3, 4, 5. Find A complement, B complement, A complement intersection B complement, A union B, and hence show that A union B complement is equals to A complement intersection B complement. This is basically De Morgan's law. So in solution, A complement, A is 2, 3. So A complement will be all the elements of the universal set other than 2 and 3. So 1, 4, 5, 6. Next we need to find B complement. So B complement is all the elements in universal set other than the elements present in B. So we are removing 3, 4, 5, 3, 4, 5, we are left with 1, 2 and 6. So A complement intersection B complement, when we take their intersection we have 1 in common and 6 in common. And next we need to find A union B. So when we take A and union of B, we are left with 2, 3. 3 is common in both. We have 4 in B and 5 in B. So this is the union of A and B. We'll take what is there in A and B and we'll put them all together. So A union B complement is 2, 3, 4, 5. Excluding these elements, we need to take the other elements. 2, 3, 4, 5. If we remove, we are left with 1, 6. So this is basically equals to A complement intersection B complement. Hence the proof. With this, we come to the end of this lecture.